Hello again, welcome to another review session. Today we're going to be going over the geometry review that we did last week in class. So let's get started. For the first problem, we need to work out the size of the angle marked x. So we're going to be taking here, we've got all the way around a point. We should remember that all degrees all the way around a point add up to 360 degrees. We're going to use this fact to solve for this missing angle. So if we see that we've got a right angle here, remember this is going to be 90. So first let's subtract this. So 360 minus 90, this is going to give us 270. Then we can subtract what we have left here. So 270 minus 145. When we work this all out, if you want to go through it, we're going to see that we should end up with 125 degrees, which will be what we have left here. So our x equals 125. Now, um, here we see that ABC is a straight line. We need to show that ABD, this is an isosceles triangle. What does this mean? Isosceles, it means that two sides are the same size. This also means that two angles are the same. So we should be able to do that here. All right, we remember this is a straight line. There are 180 degrees on a straight line. So let's see what this angle is here. If I take away 124, 180 minus 124, this should give me what? 56, right? So I know this is a 56-degree angle. All right, if this is an isosceles triangle, these two angles should be the same. This should also be 56. Now let's see if this works out. I also remember that in a triangle, I've got 180 degrees. So I know this one is 68 degrees, so I'll take 180 minus 68. This is going to leave me with 112. So this remaining degrees should be divided evenly among the two angles we have left. So if I take 112 now, I'll twist over here, 112, and I divide by 2, this is going to give me 56. So we see I get the same answer, so this proves that this is an isosceles triangle. If these two angles are the same, then that means I have two equal sides as well. So there we've gone and we've proven this. Let's move down the page. This review session is probably going to take quite a while. I highly recommend skipping to the problems that you need the most help with, and if my explanations aren't enough, come and see me in class. All right, so we see ABC is a straight line. We need to work out the size of the angle BDC. Okay, first of all, what is angle BDC? Remember, whatever letter is in the middle, this is going to be the vertex of your angle. Okay, so we know it's going to be somewhere around here. So where are the other two parts? We have B, D, C. Okay, so we're going to be looking for this angle here. All right, so how do we find this angle now? Okay, so again, we're going to use this fact about isosceles triangles. I know I have two equal sides here, so I know it's an isosceles triangle. So I'll take 180 minus 70. This gives me 110. So I know that between these two angles, I should have 110 degrees. So I'll take 110. Let's work over this side. And I divide by 2. So this is going to give me 55 degrees for each angle. Okay, so I got 55 degrees here, 55 degrees here. Okay, now I can figure out this angle using a straight line. I'll take 180 minus 55. This is going to give me 125. So I know this angle here is 125. And now, I know I'm just missing one last angle of this triangle. So I can add up these other two. It's like 125 plus 29. This is going to give me what? It's going to give me 154. And now, so if I take 180 minus 154, this is going to give me 26. So I should see that this angle here is 26. The other way I could do this, here I have 29, I have one angle, I have 55, another angle, and I see that this, let's make this another color, is sort of my third angle, right? And so I have part of this angle, but not the whole part of the angle. So I could just take 180 minus 29 minus 55 minus 70, and I still should get the same answer of 26. Either way, it should all work out. Okay, moving on to this one over here at the side. So we need to find the size of angle x, assuming that A, B, and CD are parallel lines. All right, so this hopefully shouldn't be so bad. Okay, so I'm actually just going to look at this transversal here, this line. I don't need the other one. I only need this one. I know this is 32 degrees. And so by using alternate angles, I know that this angle here is also 32 degrees. And since it's going to be on a straight line, I know that I can take 180 minus 32, which is going to give me 148, and that is what my angle here is going to be, 148 degrees. All right, let's move on to the next one. A, B, and CD are parallel. Again, so we have two parallel lines. We've got a transversal here that is part of a triangle. So now we need to find the size of x. What I'm going to do first, I am going to find what is the missing part of this triangle. Okay, so again, 180 degrees in a triangle. I have 48 and 35. If I add those up here really quick, 48 plus 35, this is going to give me what? 83, if I did my math right. So this is going to be 83 degrees here. Okay, I also know that if I take my alternate angles here using the same properties, I've got 120 degrees here. So I should also know that if I'm looking at this line, this 120 degrees should be the same as if I go and look at this angle, right? I drew it a little bit bigger because I've written there, but this angle, and we'll draw it bigger here as well if you want, this angle should be the same because of alternate angles. So I know that this part of this angle is 83. I just need to find what's left. So I can take 120 minus 83, which is going to give me 37. So this x here is going to be 37 degrees. All right, so it looks like we worked through the first page out of 8. I know this is a long one, so buckle in. Let's keep going. All right, for the next one, the size of each exterior angle in a regular polygon is 20 degrees. Work out how many sides the polygon has. So remember, an exterior angle, let's say I've got, I don't know, some kind of poorly drawn pentagon here. The exterior angle isn't just this whole thing on the outside. What it actually is if I continue this line from the shape and this angle between that line and the side next to it. So remember that an exterior and an interior angle together are going to add up to 180. All right, so we need to keep that in mind here. All right, there is one other fact that we need to keep in mind. All exterior angles add up to 360. So every exterior angular shape of a square, of a triangle, any shape is going to add up to 360. So if I know that every exterior angle in a regular polygon, a polygon where all angles and sides are the same, is 20 degrees, I can simply take 360 divided by 20, which is going to give me what? Well, that's the same as 36 divided by 2, which is 18. So I should be able to see here, this polygon has 18 sides. Okay, the next one, I see the size of each interior angle in a polygon is 165. We need to work out how many sides the polygon has. Okay, I'm going to go ahead and do one way here. When we get to this problem, we'll see another thing about interior angles. But here, okay, so I've got 165 degrees. So if I know that I've got 165 degrees for my interior angle, my exterior angle is going to be 180 minus that. So 180 minus 165 gives me 15. So I know that every exterior angle now is 15 degrees. So then I can just take 360 divided by 15. This is going to give me 24. So I should see that this one has 24 sides. All right, let's go ahead and erase this and let's move on. So we have the next problem, a pentagon ABCDE. So we need to work out the size of angle ABC. Remember, B is going to be our vertex, right? So we're looking for ABC, this angle, angle X. Okay, so we need to remember how many degrees there are inside of a pentagon. The way that we figure this out, we have a formula to tell us how many degrees there are in any pentagon. So we're going to take the number of sides minus 2 times 180. Okay, so this n, remember, is the number of sides. So here, for example, if we do this, we could take 5 minus 2 times 180. So that means we're going to be taking 3 times 180 Remember, 2 times 180 is 360, so if we add another 180 to that, we're going to get 540. So we should see that there are 540 degrees inside any pentagon. Regular, irregular, it doesn't matter. Any pentagon should have 540 degrees. So now we're going to use this fact. I'm going to take all the other angles we have here and add them all up. So if I take 95 plus 86 plus 117 plus 123. Okay, well, I see these two are going to be 240. 95 plus 86. Let's see, that's going to be 101 plus 80. That's going to be 181. Okay, well, let's go ahead and take 540. I'll subtract them 2 times to make this a little bit easier. Right, this will give me 300. 300 minus 181. This is going to give me 119. So my x here should be 119. All right, we're going to use the same fact we used earlier on over here. So let's erase our work. I'm erasing my work. You should not erase your work. Okay, so we see that shape A is a regular triangle, shape B is a regular octagon. Okay, so a regular triangle, in other words, an equilateral triangle, every angle is going to be equal to what? 60 degrees. In a regular octagon, well, maybe we don't remember that one offhand. So let's use our formula. Remember we said n minus 2 times 180. This will give us the total degrees inside of a polygon. So we'll take n minus 2. We have 8 sides minus 2, which will be 6 times 180. So in other words, 540 plus 540, since we remember, right? This will give us 1,080. Now, this gives us the total. In a regular octagon, all angles are the same, so we'll take simply 1,080 divided by 8, and when we take 1,080 divided by 8, that is going to give us 135. Sorry, ended up right-clicking there. So we see that every angle here is 135 degrees. Okay, so now we know, for example, this one has to be 60, this angle has to be 135, so we can find this angle here by remembering that all the angles around a point add up to 360. So if we take 360 minus 60, well, that gives us 300. Now 300 minus 135, this is going to give us 165. Well, we actually already used this fact here, right? So here, we already solved that there's 165. We know it's going to have 24 sides. So here, this one is also going to have 24 sides. Okay, let's move on to the next problem. Ooh, we're almost a quarter of the way done. Wow, this is going to take a while. Okay, so we need to describe the single transformation that maps triangle A onto triangle B. Okay, so there's only one transformation, a reflection, a rotation, a translation, or an enlargement. So we see it's not any bigger or smaller, it's not an enlargement. Translation, it should be in the same orientation, but this is somehow turned. This is going to be a rotation. Okay, so we already can see this is a rotation. I'll write that down. Okay, well, what kind of rotation? Which way did it go? It looks like somehow it went like this, right? So it's somehow moving in a clockwise direction. And it appears to have gone, what, a quarter of a turn, right? So this would be 90 degrees. So a 90-degree clockwise rotation. Are we done, though? No, we are not. We need to find where it rotated around. Where is the center of rotation? So if this is the part where it'll be a little messy, we can do a bit of guesswork. So if I want to say, did it rotate from here? Let's see. So we can try to figure out how close this is to, for example, the right angle and the right angle. So if I go here, the path from this point to the right angle will be up 1, 2, 3, and over this way. And this path rotated 90 degrees, 1, 2, 3, and up 1, does not touch our angle there. So we're a little bit off. But it looks like if I follow something there, I might be pretty close. So let's try again. This time I'm going to try at 1, 1. Actually, I take that back. I'm not going to try at 1, 1. I'm going to try at 0, 1. So if I try at 0, 1, for example, Let's try again. So here I would go up 1, 2, and over 1. Here, if I go up 1, 2, and over 1, oh, nope, now I'm still not there. This doesn't work. Let's try one last time. Let's try now here at 1, 0. So for this one, I'm going to go up 1, 2, 3, and over 1, 2. This path rotated 90 degrees. I would go over 1, 2, 3, and up 1, 2. Now I'm touching both of these corners with the same path, rotated, so I can see that this is going to be my center. So here the point is going to be 1, 0. So rotation, clockwise, 90-degree rotation about the point 1, 0. Okay, let's move on to some more transformations now. Okay, so here we need to reflect triangle A in the line XY. Okay, the line XY, if you don't remember, we can think of it with an example, okay? So if y equals 1, and I know x equals y, that means that x has to equal 1 as well. So in other words, I'm going to have the point 1, 1, right? If y equals 2, x equals 2. If y equals 3, x equals 3, and so on. So you're going to see pretty quickly that I've got a straight line going up diagonally here. And so now all I need to do is don't think about your shape, but rather think about your corners, think about your points, and see how far away each one is from the line, and go that same distance on the other side. So here, for example, this one I can see is 1 away, so I'm going to keep going in the same direction, 1, and put a new point. This one is 1, 2.5 away, so I'm going to go a half, 1.5, 2.5, and put a point there. And this one, 1, 2.5, 1/2, 1.5, 2.5, and I'll put a point here. And now I can finally connect these 3 points, and I've got my new triangle. Over here, we need to describe the single transformation. Okay, we see that A is much smaller than B, so we can see this is going to be some kind of enlargement. But we need to say 2 more facts about our enlargement. We need to say how much bigger it is and where the center of enlargement is. So if we take a look here at our proportions. Okay, so this side is 1. The similar side would be 2. So we can see that this is a scale factor of 2. Now, where would the center of enlargement be? A quick way to find this out. So if it's 2 times bigger, let's see. Again, let's go ahead and take our similar corners into account. So if I take this bottom right angle here, I'm going to see that it's 1, 2, 3, 4 away from this one, and it's all in a straight line. So I'm just going to take this path, to straight by 4, and double it. I'm going to go the same way, but in the other direction. So I'm going to go 1, 2, 3, 4. And that would be my point. If I want to do that, for example, here with these, let's use a different color. So I can see this one is 1, 2 up, and 1, 2, 3, 4 right. So to go 4, 4 left, down 2, I could do the same thing here. 1, 2, 3, 4, and down 2, and I still get to that same point. So this is going to be my center of enlargement. So what point is this? This is going to be the point -7, +1. So -7, 1. So it's an enlargement, scale factor 2, with the center of enlargement at -7, 1. Let's translate this triangle now with the vector 5, -3. Remember, when we have vectors, the number on top is going to tell us how our x moves, the number on bottom tells us how our y moves. So if it's positive on top, we're going to move right. If it's negative on top, we'll move left. If it's positive on bottom, we'll move up. If it's negative on bottom, we move down. All right, so here we see we've got +5. Let's go ahead and take a look at our corners. I always suggest looking at corners, not so much at anything else. So I'll go right 1, 2, 3, 4, 5. I'm not done yet. Now looking at the number on bottom, I have -3. That means I'm going to go down 3. So 1, 2, 3. So that's where my new corner is. Looking at this one, again, I'm going to go to the right. 1, 2, 3, 4, 5, and down 3. 1, 2, 3. Put a point, and I can do the same thing here. Or since I kind of have an idea of my orientation already, I can see this is 1, 2, 3 up from my bottom point, so I could go 1, 2, 3. I could do that here, although, again, the point-by-point method is the safest, although if you feel confident doing that, that method is also okay. And finally, we have shape A is transformed to shape B by a reflection in the x-axis. The x-axis is this one, so in other words, we had a mirror from here to here, and it's followed by a translation. By a translation, I cut that off the screen, didn't I? By a translation PQ, I think it says. So we need to find the value of P and of Q. So if I move this down, the first part I have these, so again, go down 2, that means I'm going to go down 2 more, down 2 more, 1, 2, 3, 4, so down 4, and again 1, 2, 3, 4, 1, 2, 3, 4. So when I did the first translation, the reflection, the first step was there. So now I need to figure out how this moved to B. So let's go ahead and take this far left corner. To get to this corner, the same relative one, I had to go up. I had to go 1, 2, 3, 4, 5 left. So remember, going left, I'm going to have a negative 5 on top, and I had to go up 1, positive 1. So P was negative 5, and Q is positive 1. Okay, so here we have the next one. We're going to move on to a different area of this. We're going to actually talk about area. So the diagram shows a trapezium with an area of 30 square centimeters and a perpendicular height h. So we need to find the value of h. Okay, so how do we find the area of a trapezium? We take, if this is our base 1 and this is our base 2, we're going to take base 1 plus base 2 divided by 2. In other words, we're going to find what number is in between these two and multiply it times the height. Okay, so we know that in this case 30 is going to be somehow equal to 3 plus 7 divided by 2 times h. So 3 plus 7 is 10. 10 divided by 2 is 5. And so if we take both sides and divide by 5, we're going to quickly see that h equals 6. So h would be 6 centimeters. All right, moving on to some more area. Okay, so here we have a right angle triangle and a parallelogram. So it says here the area of the parallelogram is 4 times the area of the triangle. All right, so let's go ahead and set up what we know then. So how do we find the area of a parallelogram? We're going to take the base times its height. Area of a triangle is going to be base times height divided by 2. So we can already figure out what is the area of the triangle, right? So we're going to take 7 times 4 divided by 2. And they said that we know that this is going to be the same thing if we take this times 4, right? 4 times the area of the triangle is the same as the area of the parallelogram. So 14 times h. So let's work this out now. So 7 times 4, well, we can already cancel this, right? 4 divided by 2 is going to give us 2. So 2 times 7 times 4 equals 14. Well, sorry, 14 times h. Well, I'm going to do a quick little trick here. I see that this is already 14, right? So if I divide by 14 already, I can just cancel these. And I'm going to see here that leaves 4 is being equal to h. So my height of the parallelogram is 4 centimeters. Let's erase some of this work for the next problem. Okay, so here we need to work out the area shape. So it looks like we've got a rectangle and a triangle. So first, the rectangle we should know pretty easily. We take our base times our height. So 7 times 5, this is going to be 35 square centimeters. So we know that this is also 5. This is 4, so we're going to take base times height divided by 2. So in this case, 5 times 4 divided by 2, which is going to give us 10 square centimeters. So we have 35 and 10. So we're going to add them all together. 35 plus 10 equals 45. So we're going to have 45 square centimeters for this shape. Moving on down here, back a little bit back to angles. So ABCD is a parallelogram. Angle DAE, so is 63 degrees, marked here. Angle BCD, marked here, is 124, and angle CBD is 25 degrees. We want to figure out what is the size of angle X. Okay, so we know that, for example here, this is going to be the same as if I were to take 24, 124, right? So I could take 124 minus 63. This is going to give me 61. So I know that this part here is 61. All right. Now, this part might be a little bit trickier, but how many degrees are there in a quadrilateral? We know that in total we should have 360, right? Okay. I also know, for example, if I got 25 here, these are parallel lines. By using alternate angles, this should also be 25 degrees, right? Okay, so one way I could do this, if I know this is 63 and this is 25, I could figure out what's left, 180, right? Since I have a triangle here, minus 63 plus 25, that's going to give me 88, which would give me 92. So I know this is 92. This is on a straight line, right? As you can see, it's not drawn very accurately. Sorry, one moment. Okay, sorry about the interruption. Okay, so as I was saying, you could see that here we got 92. As you can see, it's not drawn to scale. We have a straight line here, so this should, in theory, be what? 88 degrees. Okay, so in theory, 88 degrees is our answer, right? Having walked through, you could do this a number of other ways as well. You could again see here you got 124 plus 25, 180 minus this together, 149 is 31. Again, we know because of the alternate angle, this should be 25 here, right? We also know then that this would be 31. You could then work that out from other ways that this is 88 degrees. Okay, so moving on. Halfway through, all right. We got some big numbers coming up eventually. Okay, so we have a triangle here. The triangle has a rectangle inside of it. The triangle has a base of 12 and a height of 10, and the rectangle is 3 by 5. So we need to work out the area of the shaded region, the gray part. So let's find the area of the triangle first. We're going to take our base times height, 12 times 10, divided by 2, which will give us 60 square centimeters. And here, this is going to give us 15 square centimeters, right? Base times height. So we just need to take 60 minus 15. So we get 45 square centimeters. Okay, next one. The circle has a diameter of 12 millimeters. So if this is our circle, remember the diameter is the line that goes all the way across the middle, right? And it's going to be 12 millimeters. So we want to work out first the circumference of the circle. So the circumference of the circle, remember there's a formula. It's going to be 2 times pi times the radius. But remember, the radius is just half of the diameter, so we could also say this is like pi times the diameter. So here, we're simply going to take, if we give our answer in terms of pi, 12 times pi millimeters. And we're done. Not so bad, right? Okay, next we have a cuboid. We want to find the surface area of the cuboid. Let's go ahead and erase our circle work. This will take a little bit more area. So to find the total surface area of the cuboid, we're going to take all the sides, we're going to take the area of all 6 sides of this. So this side, for example, we have 12 times 4, right? So 12 times 4. So this side has an area of 48 square centimeters. This side on top, again, this is going to be 5, this is 12. So we take 12 times 5, which is 60. And over here, this side is 4 by 5. So we take 4 times 5, which is 20. Okay, and then we're going to see the back sides, the left side and the bottom side, are all identical to these 3 numbers. So we could add these up and multiply it by 2, right? So 48 plus 60 is 108, plus 20 is 128. We'll just multiply that by 2 really quickly. So we end up with 256. And since, again, we're talking about area, our units are going to be squared. So we have square centimeters. Okay, so now we're going to do some more surface area, but this time of a triangular prism. Okay, we need to be a little bit more careful here. We can't just double our sides like we did before. We need to find the area of every side and add them all up together. So here we've got, for example, this side is 5, this side is 12. So to find the area of the triangle, take 5 times 12, divide by 2. This is going to give us 60 divided by 2, which is 30. So this one is 30. The triangle on the back, on the other side here, is also going to be 30. The rectangle here on the bottom is going to be 12 times 10, which is 120. The rectangle on the back here, again, this line is 10 centimeters times 5, which is 50. And this rectangle here on the front, this big rectangle along the hypotenuse, is going to be 13 times 10, which is 130. So when we add these 3 up, 120 plus 50 plus 130, we're going to get 300. But we can't forget about our 2 triangles, right? So plus 30 plus 30 plus 60, we're going to get 360 square centimeters. Okay, now we have a prism where the cross section, or the end sides, are trapeziums. So we want to work out now the volume of the trapezium. So if we want to work out the volume of any trapezium, we're going to work out what's called the cross section, which is a shape that if you take a slice out of the middle, is going to be a normal 2D shape, which is identical to both of its endpoints. So if we find the area of the end, we can take the area of the end and multiply it times the depth, or the height, whatever you want to call it, and that's going to give us our volume. So first let's find the area of the trapezium. Remember, area of the trapezium is going to be base 1 plus base 2 divided by 2 times the height. So here, that would translate to 4 plus 8 divided by 2 times 7. Okay, so 4 plus 8, that's 12. 12 divided by 2 is 6. 6 times 7 is 42. So we have this trapezium has an area of 42 square centimeters, which we now multiply by the depth, let's call it. So we'll take 42 times 10, which is 420. So the volume of this prism is going to be 420 square centimeters. Move a bit further on down the page. Okay, now we have a cuboid, A, B, C, D, E, F, G, H. We see that ABCD is a square with an area of 25 square centimeters, and that GC, this line here, is 12 centimeters long. We want to find the volume. So the way that we can do this, we can either realize that we're taking the square, which is a cross-section, and multiply it, already just multiply it directly by 12, or since it's a square, we know that both sides are 5 centimeters, 5 centimeters, which will then just multiply by together to get 25 anyway. 5 times 5 is 25, then times 12. So either way, we end up taking 25 times 12, which should give us 300. So our volume here is going to be 300 cubic centimeters. Okay, now we have a cylinder, which is going to be a little more complicated, but at least here we can give our answer in terms of pi. So we have a cylinder with a radius of 5 centimeters and a height of 12. We need to find the area of the end piece. We need to find the area of the circle. So remember, the area of a circle is going to be pi times the radius squared. So here, we're going to take, what is our radius? Our radius is 5. So we'll take pi times 5 squared, which is going to be 25 pi. And to find the volume now, we just take this end piece, this cross-section, times the height or the depth. So we'll take 25 pi times 12, which is going to be the same calculation as before, only with pi. So we get 300 pi. So our answer is going to be 300 pi centimeters cubed. We're dealing with volume, remember? So it's going to be in cubed. All right, getting closer. Almost done. Now we have something that's even a little bit trickier in my opinion. We have surface area of a cylinder. So we're going to have to find the area of the circle. Let's go ahead and start with that. So remember, area of the circle is pi r squared. So our radius this time is going to be 6 meters. So we're going to take pi times 6 squared, which is 36 pi. So the circle on bottom is 36 pi. The circle on top is 36 pi. So we have two sides that are 36 pi. Now I'm going to leave these here for now because next I need to find what is the area of this thing that wraps around. First of all, so we know the height is 7, but if we cut this and make this one giant rectangle, what will be the length of this side? We need to find the circumference. So remember, the circumference is going to be like 2 times pi times the radius. So here, remember, that's going to be, so 2 times pi times 6, which is going to give us 12 pi. So that's going to be the circumference. Don't forget, though, we're looking for the area of this sort of rectangle that we get, that we kind of bend to get our cylinder. So we'll take 12 pi times 7, which is going to give us 84 pi. And finally, we're going to go back to our two circles and add them all in here. So we add these all up. So 84 plus 36 plus 36. That's going to give us 156 pi. So our surface area is going to be 156 pi. Sorry, we're not in centimeters anymore, we're in meters. So 156 pi meters squared. We're dealing with area, so remember it's going to be squared. Okay, let's go ahead and erase this word, move on to the next. We didn't talk too much about plans and elevations this year. So here, really quickly, a plan is going to be if you take a 3D shape and look at it from the very top. So this is like you're on top of it looking down. An elevation is looking at it as if you're standing in front of it or by the side. So the front is if you're standing in front, looking at it horizontally from the front, and the side would be, again, looking at it horizontally from the side. So we have this shape here. Okay, we see that here we've got some kind of edge, right? And by looking at the front elevation, we can see that's likely these two edges. So we're likely looking at, this is going to be sort of, right? So we could be standing here, looking at it as if we would see this, and if we're looking at it from above, it's going to look like this. And so from the sides, again, we can't really tell what's what because it's all going to be basically one inclined side going up. So we want to give a sketch of the solid shape. So let's do our best to draw this, okay? So we're going to have some kind of trapezium, we know that. And whenever you're drawing prisms, I always recommend drawing two of the same one and then later just connecting your sides. Again, I'm no artist, but you should hopefully get the idea of what I'm drawing. But we also want to give the dimensions here, okay? This is drawn on a centimeter grid, so that means that 1 square is 1 centimeter. So the base of this is going to be 4 centimeters, right? Here at the top, this is going to be 2 centimeters, and the height, or the depth rather, is going to be, well, you can say the height is 2 centimeters as well, and the depth is going to be 3 centimeters. All right, getting closer and closer. Okay, we need to calculate now the length of BC, and giving our answer correct to 1 decimal place. Okay, so we've got a right angle triangle. That should hopefully make us think of our old friend Pythagoras. We're going to use the Pythagorean theorem. Right? A squared plus b squared equals c squared. Remember, the c squared is always going to be the longest side across from the right angle. So here we know that 6 squared plus, we're going to call this our b side, b squared equals 14 squared. So this is the same as saying 36 plus b squared equals 196, right? So we're going to go ahead and move this over. You see that b squared equals 160. And if you put this into your calculators, square root of 160, you should end up with about 12.6, right? Because we'll take the square root of both sides now. So b equals, if we round, 12.649 according to my calculator. But since we have 6.4, this is going to round down to 6. So b equals 12.6 rounded to 1 decimal place. All right. Just a few more questions and we're done. Almost there, almost there. Okay, so here we want to write 35 cubic centimeters in cubic millimeters. So remember, since we're dealing with cubic units, if my normal conversion of centimeters to millimeters is times 10, here in cubic units it's going to be times 10 cubed. So here, this would be 35,000 cubic millimeters. Same over here. So normally meters to centimeters, my conversion is going to be multiplying it times 100, right? 4.5 meters would be 450 centimeters. But since I'm in squared, I'm also going to square the conversion. Oops. Square the conversion. Okay, I'm touching the screen too high, it looks like. So I would take 4.5 times 100 squared, which is 10,000, right? And I'll end up with 45,000. So this will give me 45,000 square centimeters. Okay, next, a sprinter runs a distance of 200 meters in 25 seconds. Work out the average speed of the sprinter. So remember our speed formula, right? Okay, so let's figure out how many meters he runs basically in 1 second. So we take 200 divided by 25, which is going to give us 8. So we can see that he runs 8 meters per second. Okay, next we want to work out the density here. So we have a 760 gram piece of gold with a volume of 40 cubic centimeters. So we want to work out the density. So again, we're just going to take 760 divided by 40, which is going to give us 19 grams per cubic centimeter. And finally, we're on to our last question. All right, we have a travel graph where Emily goes to the beach. She stays at the beach and she goes back home. Nice day out at the beach. So we see that she leaves her house at 2 p.m. She gets back at 5 p.m. So not a very long trip. So let's see, how many minutes did Emily stay at the beach? So we're going to assume that this is the beach. We see what she got here at, what, 2:45, right? 14:45. And what time did she leave? She left at 4 o'clock. So we want to go ahead and figure out how much time this was, right? So this would be 1 hour and 15 minutes, but they're asking only minutes, so this will give us 75 minutes, right? 60 minutes of 1 hour plus 15, so 75 minutes. Now we want to figure out what Emily's average speed was on her journey to the beach. Okay, so we'll see that it is 35 miles away, and it took her 45 minutes to get there, right? So in other words, it took her 3/4 an hour to go 35 miles. All right, so there are different ways we can do this. We could, in theory, continue this line up and sort of estimate, or we can actually, calculate this out. So we could take 3/4 an hour times 35, sorry, rather 35, forgive me for the mistake there. All right, we're going to take our distance divided by time, so getting it all backwards now. So our distance would be 35 divided by our time, right? We're going to put this in miles per hour. So divided by 3/4. So 35 divided by 3/4 is going to give us, well, if we want to do this as a fraction, this would be times 4/3, right? So give us what ends up working out as 46 2/3. If you put this in your calculator, you could take this divided by 35 divided by 0.75, and you'll get 46.7. So her average speed would be 46.7 miles per hour. And that's it. We're finally through this practice exam. If you have any other questions, please let me know. I hope this was helpful, and I will see you all again in class. Have a good evening.